Good morning, everyone. My name is Andrea Locatelli, and I will giving a short lecture as an introduction to X-ray spectroscopy and microscopy. Let me first put this presentation in display mode. There it goes. And let me thank the organizer of this event, and in particular Salma Baghdadi, who did an excellent job organizing the meeting. So the meeting is hosted by CERIC at Trieste. Sorry? Okay. The meeting is hosted by CERIC in Trieste. And as you know, in Trieste, we have a Synchrotron, which is a third generation Synchrotron, which operates since 1994. It has been upgraded several times. And the Elettra Synchrotron hosts a really huge number of users every year. They come here to perform a number of experiments which are approved by independent panels from Elettra and from CERIC, and they basically use radiation in a very broad spectral range, which really goes from the infrared to the hard X-rays, through the ultraviolet, and especially soft X-rays, as a ring which can operate at 2 and 2.4 GeV. Electra is particularly suited to produce soft X-rays. And soft X-rays of this kind are just great to perform a number of spectroscopies. Today, I will mainly concentrate on photoelectron emission and absorption spectroscopy. But of course, you can employ the same spectroscopy to perform different kinds of experiments, and in particular imaging, and thus microscopy, and of course also diffraction. Sorry, okay. So why are we so keen of performing experiments in material science using synchrotron light? Well, of course, because synchrotron light allows a very high intensity to be delivered to your sample, which means that the experiments can be done quickly. And sometimes you can follow a reaction in real time. Of course, synchrotron light is tunable, which means that you can choose let's say, the color, so the frequency, the energy of your photons. And as I already introduced, there is a very broad spectral range. The other very useful properties is that it allows a narrow angular collimation, which means that you can build a smart optical system to deliver the radiation to your sample. It is coherent, which is very important in other microscopy applications. It has a high degree of polarization, meaning that you can control the polarization in the plane of the orbit. Perpendicular to the plane of orbit, you can have it circularly polarized, left or right-handed. And of course, being a synchrotron, it's not a continuous light source, but it's a pulsed. It has a pulse structure. That means that basically, experiments can exploit the duration, or better, the very low duration of synchrotron light pulse, which is about, let's say, in the range 60 to 150 picoseconds, depending on the operation conditions of the machine, to perform stroboscopic experiments. But the reason why you want to do experiments, and probably you have already learned that it's not that easy to perform experiments, is that you want to be quantitative. And synchrotron radiation allows you to be quantitative. It means that you're measuring a certain observable, which is typically a function of the energy of the photon, of the polarization of the photon, of the angle of incidence of the photon beam on the sample. And then, especially when you do spectroscopy, you measure, for example, electrons. And when you measure electrons, you basically measure the kinetic energies of the electrons. You can also measure the polarization, their angle of emission from the surface. And of course, if you do microscopy, you have to measure something which is very trivial. So the different properties that you find across the sample. And in general, nature presents inhomogeneous material. And this is why it's interesting to perform this kind of experiments. So let me introduce the first spectroscopies and photoelectron spectroscopy basics. Well, the process is very simple, and it's based on the photoelectric effect. Basically, you shine X-rays on the sample, and then photoelectrons are emitted. And if they have enough energy, they can leave the sample. And then, of course, there is a whole technology of energy filters, which allows you to measure their kinetic energy. And from measuring the kinetic energy, you can easily determine the binding energy of the electrons. This kind of spectroscopy is mostly concerned with two different types of electrons, electrons emitted from core levels and electrons emitted from the valence bands. If you use the first one, then it is also known by the name of ISCA, or electron spectroscopy for chemical analysis. At least this was the first name chosen by or proposed by K. Sigban, who actually received the Nobel Prize for developing XPS into a major tool for surface analysis. Now, the great thing of XPS is that not only it's element specific, but it really provides a wealth of information about the chemical environment surrounding the emitter. Of course, if you instead if you instead probe the valence band, then you have an incredible tool to characterize the electronic structure of surfaces. And of course, here you can also do diffraction. And this is XPD, X-ray photoelectron diffraction, is a very powerful technique to determine the local structure around the emitter. Now, let me give you some practical example of the power of synchrotron light concerning tunability. This was an experiment concerned with growing graphene on ruthenium, a model system for having a certain type of interacting graphene. And the point is that the ruthenium 3D core levels, and in particular the 3D 3/2, is kind of close to the carbon 1s peak, which was used to measure the amount of carbon and the chemical state of carbon in the early stages of the graphene growth. You see here on the left-hand side, which we have the photoionization cross-sections for the carbon 1s and the ruthenium 3D. And note that there is a logarithmic scale. And at some point here below 400 EV, the cross-section of the ruthenium 3D decreases a lot, while the carbon cross-section increases. And you can see this in the graph on the right-hand side. At the beginning, at 370 EV, you barely see the carbon, and you see the doublet due to ruthenium 3D. But then as you go down with the photon energy, then you become immensely sensitive to carbon. And this is a very, very powerful means to perform an experiment. The other tool that we frequently use and is very often available on beamlines which are specialized in X-ray photoelectron spectroscopy, it's actually X-ray absorption spectroscopy. And as you can see here, well, there are energy-dependent resonances which arise from transitions from core level into unoccupied valence states. And they give you really an enormous insight on the composition of the sample. You can see here some different materials starting from iron, cobalt, nickel, and then some oxides or compounds. And you see that the shape, the spectral shape of these data are terribly sensitive to the elemental composition and chemical state. And actually, the spectroscopy gives you provides you access to the electronic charge in the material, that is the valence state or the bond orientation. Furthermore, it's not illustrated here, it gives you also magnetic sensitivity. If you have a photoelectron spectrometer, you can basically tune it to the secondary emission, and in this way, you can indirectly measure the absorption. Yes, there is a very important consequence of this type of measurement. By using secondary electrons, you gain access to somehow a different depth than in photoemission spectroscopy. And this is illustrated by this classical slide on the inelastic mean free path. First case, if you use photoelectron spectroscopy and you measure core levels, then you typically measure electrons which have kinetic energies in the range, let's say 50, more than 1,000 electron volts. And as you can see here, the inelastic mean free path reaches a minimum about 70 to 100 electron volts, meaning that you're extremely surface sensitive, in the sense that you're basically sensitive to the two topmost surface layers. Of course, if you measure electrons which have kinetic energies above 300-400 eV, then you become more sensitive also to the bulk. But this is the key. X-ray photoelectron spectroscopy is a very surface sensitive technique. Instead, if you measure secondary electrons, that is in an absorption experiment, the inelastic mean free path can be significantly longer. And basically, you can probe several nanometers, let's say less than 10 nanometers, but definitely you can probe buried interfaces. Okay, this was the first part of my talk, which was basically a general introduction to the spectroscopy we use at Synchrotrons, at least on the photoemission beamlines. And I just want to focus on the beamlines we have at Elettra. Many of those are actually part of the CERIC consortium. The beamlines that you see here, Superesca, VUV, gas phase, Aloisa Bach, APE, low energy, and others are specialized really in XPS, XAS, and ARPAS. And after this, I would like to introduce, of course, these beamlines are not microscopes. Now I would like to focus on microscopy and introduce you to the two methods which are used in microscopy. The first one is that of X-ray photoemission electron microscopy. It's actually a method which dates back to the 30s, and it became more and more complex during the years. Essentially, this is a direct imaging parallel detection method, or you can call it full field microscopy. The beamline photons, or whatever light source that you may consider, for example, a laser or a mercury lamp, it's focused on the sample, photoelectrons are emitted, and then you have a more or less complex piece of electron optics which produces a magnified image of the sample on a two-dimensional imaging detector formed by an MCP coupled to a phosphor screen and then CCD for computer acquisition. So here the lateral resolution is determined by the electron optics, and mostly it's the first lens, the objective lens, that determines the performance of the instrument. Of course, in the back focal plane of the first lens, the objective, you can find the diffraction pattern, and typically the optics produces other images of the diffraction pattern, and you can put an iris there, and then you can decrease the angular acceptance of the instrument, which has some consequences on the lateral resolution. This instrument can come in combination with other techniques like low energy electron microscopy and LEAD. It has an intermediate spectroscopic ability, and it can work up to the high 10 to the -5 millibar range. The other approach that is used to perform microscopy is that of scanning photoemission electron microscopy. And here you use something completely different. You use a special X-ray optics, which are called Fresnel lens. You focus the beam into a microspot or a nanospot better, and then you raster the beam on the sample by scanning the sample state. Of course, you can use an electron analyzer and collect the photoelectrons emitted from the surface at grazing incidence, or if you have very thin samples, you can work in transmission. Due to the fact that you can use, let's say, a conventional electron energy analyzer, this technique gives you an excellent spectroscopic ability. There are even high pressure, or let's say near ambient pressure variants of this technique. And whereas PEEM is suitable for working only with flat surfaces, here you can also work with rough surfaces and image things which are, let's say, complex for the PEEM, like nanotubes. Just a brief amend. I think I just want to tell you, in the PEEM, the resolution has always to be traded with transmission. You can see here in the view graph, basically a figure which quantifies the circle of confusion created by a point source. And depending on the diameter or the radius of the contrast aperture used in the PEEM, it basically is very high for low diameters, meaning that this is a very, very small aperture, and the reason is because of diffraction. Then it reaches an optimal value, and then as you increase the diameter of the iris and you improve the transmission of the instrument, there is the contribution of spherical and chromatic aberrations, which degrade the lateral resolution. The PEEM can reach a best lateral resolution of about 10 nanometers. But of course, there are variants which have aberration correction implemented that can improve significantly the resolution and come to about 1 or 2 nanometers. In the case of the scanning photoemission electron microscope, this is the focalizing lens, the so-called Fresnel lens, and the resolution is determined by this delta R here, which is the width of this of the tiniest transparent ring, because the lens is formed by alternating transparent and opaque rings, and it actually has some focusing properties similar to those of the conventional optics, but the resolution is really determined by how thin you can make these concentric rings, which are fabricated by lithographic techniques. At Elettra, we also have spectral microscopes. Like there is one spectral microscopy beamline, which is dedicated to ARPAS. SC microscopy is instead dedicated to, I would say, chemical imaging. Nano-SC is a PEEM, which very often performs ARPAS experiment and then nanospectroscopy. These beamlines are mostly active in these areas, essentially material science, nanotechnology, and energy-related topics. Of course, we study these topics by focusing on what we call model systems. However, there is a tendency to try to study realistic cases of devices, and this is a very important trend in photoelectron spectroscopy. I want to give you some examples. I think I have more or less a quarter of an hour to finish my presentation. This was an experiment performed at the Super ISCA beamline, and the researcher wanted to grow perfect graphene layers, which are just single layer thickness, which can be done, as I introduced before, on the ruthenium 001 surface. The point is that there is not much use of having graphene on a metal, but in principle, you would like to have it on silicon, which is the material which is most frequently used in conventional electronics. And in order to achieve this, they basically expose the surface the surface of ruthenium already covered by graphene by a flux of silicon atoms, which intercalated under the surface. And actually, in this view graph, you can see the spectra of ruthenium 3D and carbon 1s as, let's say, during the deposition of graphene. And you see here where it becomes bright yellow, the growth of graphene. And then at some point, they also expose it to silicon, and you can clearly see that the initial configuration of ruthenium shows at the end the presence of the formation of ruthenium silicates. As a second step, this surface was exposed to oxygen, and this oxygen was able to intercalate under graphene and oxidize the silicates and produce a layer of silicon oxide, which you can see in this graph here. So a very complex experiment, which basically starts from clean graphene over ruthenium, and then forms ruthenium silicate, and then by exposition to oxygen creates silicon oxide under graphene. And this kind of layer can be, let's say, at least in principle, transferred on a different electronic device. It's a microscopy beamline. I will give you just one example. This is a scanning microscope which operates in the energy range 400 to 1000 to 1200 eV, and allows a pretty decent energy resolution of about 180 milli-electron volts. The spot size on sample approach is really 100 nanometers, which is the resolution of the microscope. And I think they are doing great things nowadays because they adapted their microscope to be able to perform experiments in what we call near ambient pressure conditions. Basically, they have a special sample holder where which allows gases to enter in close contact with the surface. And there are tiny holes which allow the X-rays to reach the sample and the photoelectrons to reach the energy analyzer. And in this way, even if the local pressure at the sample is close to 1 millibar, they can still keep their UHV apparatus in high vacuum and obviously being able to operate using standard operation. And here on the right-hand side, you see copper crystal on which there are dark places, which are graphene island, and they expose it to oxygen to check how the surface becomes oxidized at, let's say, near ambient pressure. And you clearly see that the copper is probed by this Auger peak here, and where you see the let's say a yellow color, it means that the surface is still metallic, whereas the oxide is rendered in violet. As you can see here, the evolution for growing oxygen pressures, you can really see that the places of the surface which are not covered by graphene are oxidized first. It really illustrates well the fact that graphene, it's a very effective oxidation, or let's say, prevents oxidation. So, of course, they can do more complex things. They use graphene cells to study liquids, for example, because graphene can prevent the liquid from evaporating into the vessel, but it's a membrane which is transparent to electrons, to photoelectrons. And in this way, they demonstrated they can collect XPS spectra from a silver nitrate solution. They can study the radiolysis of water, which was contained in a special sample holder called multi-window graphene array. It's formed by tiny capillaries which are filled with a liquid and a solution into that, and they were able to basically study an electrolyte and applying voltages to this setup here. And finally, of course, another method is just to include the liquid under a bubble. So time is flying. I will skip some slides. Just an example of the spectral microscopy beamline at Elettra. Here we have a Schwarzschild objective to focalize the beam on sample. The beam spot has a size of about 0.6 microns, and the beamline works at basically two energies, which are 27 and 24 and 74 eV. This beamline is mainly used to perform ARPES experiments, and of course it has a very complex and effective sample stage, which can be cooled to liquid helium temperature. It reaches at the moment 35 milli-electron volt energy resolution, but it will be soon upgraded to be able to reach the state of art. That is energy resolutions below 5 milli-electron volts. And a very interesting experiment that they are doing is basically they do study devices under operation. Now, the trick to be able to study these devices is to start from an insulating substrate, silicon oxide, and then put, for example, two electrodes, which are platinum made on this kind of surface, and connect the material they want to study, which are typically some layered materials like graphene, and apply a voltage across them. So in this way, they can basically pump charge into the material and change the valence band. And this technique is called electrostatic gating. You can see here the principle in A, then you can see the real device in B. You can see also a optical microscopy of the same material here in C. And then here in D, you see a microscopy image, which actually shows the silicon oxide in blue. And as you apply gating voltage to the device, you basically inject charge. And so you're basically shifting. You can, in this way, at zero voltage, there is no, this is the normal pi band of the graphene. But if you inject or remove charge, then you can actually see the electronic structure of the system in different conditions. And the graph here on the right-hand side is particularly important because this is a method that allows you to see states that are normally not occupied. And this is a more significant case of the conduction band edge in tungsten selenide, where the same trick was used. You can see here, this is the same setup. Rather than instead of graphene, you have tungsten selenide. And they wanted to see and compare with the theory the electronic structure of 1, 2, and 3 monolayers. And the particularly important thing is that injecting charge here, they were able to shift downwards at higher binding energy the bands, and they were able to image in this way the conduction band edge. So very, very quickly, the last technique that I want to introduce is the PEEM at nanospectroscopy. This is a PEEM microscope, which can work with, of course, with the beamline photons, but this instrument also includes a low energy electron microscope. And whereas the first one gives you access to the chemical properties using microspot XPS, imaging XPS, and microscope spot ARPS, then you can use the low energy electron microscope to learn about the surface structure. I just want to illustrate the principle of low energy electron microscopy. Basically, you have a beam of electrons, which is collimated and directed toward the surface. Backscattered electrons are then used for imaging. And due to the very high probability of cross-section, you have really a huge signal that you can use for imaging. And this is the growth of cobalt on rhenium. And you can see that layer by layer, we can follow the evolution of the growth. So in different colors here, you see in blue, 2 layers, in yellow, 3 layers, and so on. So we can very precisely follow the thickness and the structure of a sample, which is then characterized using X-rays. I feel that my time is really off, and I want to give you just one example of this technique. PEEM is very often used in magnetic imaging experiments. So these experiments are performed basically exploiting X-ray absorption spectroscopy and combining it with X-ray magnetic circular dichroism. In this way, we can basically, by simply measuring images with opposite photonelicity, we can image the magnetic domain into ferromagnetic material. I just want to mention that we measured the first stable skyrmion at room temperature. It was confined in this tiny structure composed by a 3-layer platinum cobalt on magnesium oxide, and it has a non-trivial magnetic structure that you can see here. You can also use this technique to look at nanowires, and here in this image you can see a nanowire, which is actually here, with the magnetization oriented radially, and you can see here the shadow of the nanowire. And this kind of tomography experiment enables you to really to detect the magnetic configuration of this kind of nanowire. So time is off. I'm completely sorry for having to skip so many slides. I want to make a summary about the beamlines that I've been through in this quick overview on the capabilities of the techniques at Elettra. SuperESCA is specialized in fast XPS and high resolution XPS. ESCA microscopy has capabilities for inoperando experiments, especially at near ambient pressure. Nanospectroscopy reaches nanometer range lateral resolution. LIM is a very useful preparation technique for growing in situ samples using surface science methods. And indeed, there are multi-method possible, and magnetic imaging using magnetic circular dichroism is really one of the main applications. And then there are a range of beamlines like upper-low energy, nano-ESCA, and spectral microscopy, which are specialized in ARPAS. In particular, upper-low energy and nano-ESCA are equipped with spin filters, which enable really to look at the spin-filtered electronic structure. So I would say I gave, you can find some references in the slides, and I would like to stop here to enable at least 6 minutes of questions. Thank you very much.